Hello, and welcome back to my YouTube channel. My name is Professor Govalla, and today I'm going to be talking to you about the common source N-channel MOSFET. And essentially, we're going to analyze the small signal model of this configuration and find the input resistance, the output resistance, and the total AV gain of the amplifier. And to begin, let's start off by listing some currents. So here we have IN coming in from VN. We have an RO right here as well. And let's call this RO1. And RO comes out and goes to ground as well. So with that being said, we can talk about the RN, the input resistance or input impedance, which is equals to Vn over In. And we know that In is equals to 0 simply because no current flows through this gap because it's an open circuit. So no current flows through it. So In is 0 and Vn is equals to VGS. You can also see it from here. They're in parallel. So Vn and VGS are in parallel, so they're equal to each other. So as a result of that, Rn is equals to VGS over 0, which is approximately infinity. So that's your Rn resistance, your input resistance, which is going to be infinity. We can then go ahead and solve for Rout, where Rout is VO over IO, where when Vn is equals to 0. So what I'm going to do here is I'm going to consider a closed circuit here. All right, closed circuit here, and we then do a KVL on this loop. Let me use a different color. Let me use purple. Use a KVL on this loop right here. So again, we can say that VGS, and we can also do a closed loop here as well. We could say that plus VGS is equals to 0. And then loop 2, we can say that IO, if we do a KCL, IO is equals to GM VGS plus IO1. Again, this KCL says that this IO coming in here is equals to this current going here and this current coming in here. As a result, we know VGS is equals to 0, so this goes to 0. And then IO is equals to IO1. So we could say that this is my first equation and this is my second equation. And my third equation will be this KVL in this loop through loop 2 right here. I'm going to change colors. And I'm going to say minus VO because the voltage across here is VO. So minus VO plus ROIO1 is equals to 0, right? That's the voltage drop across this resistance. So plus ROIO1, right? That's equals to 0. We can solve for VO and say that VO is equals to ROIO1. And we know that IO1 is equals to IO. So VO is equals to ROIO. As a result, VO over IO is equals to RO. And this is equals to Rout. So the output impedance or the output resistance of this common source NMOS is RO. Lastly, we want to find the AV gain, and I'm going to do that up here so we could see the small signal circuit. And what we're going to do is we're going to reapply my input voltage, Vin. So if we consider that AV is equals to VO over Vin, we can start with the KVL at loop 1 right here. So minus Vin plus VGS is equals to 0. So VGS is equals to Vin. And this is my first equation. I can do a KCL with my IO, my output currents. So let's do an arrow here, an arrow here. So IO is equals to IO1 plus GM VGS. And then let's solve for IO1, which is equals to IO minus GM VGS. This is my second equation. And lastly, let's do a KVL at loop 2 right here. And we could say that this is minus VO, right? Because the current's going into the negative terminal. So minus VO plus RO IO1 is equals to 0. So IO1, we know from equation 2, is IO minus GM VGS. So I'm going to go ahead and plug that in here. So I get minus VO plus RO IO minus GM VGS, which is equals to 0. And we then also know that VGS is equals to Vin. So from my equation 1, I'm going to plug VGS in here. And we're left with minus VO plus RO. I'm going to distribute the RO. So ROIO minus RO GM Vin, which is equals to 0. So now we have VO and Vin, but we want to get rid of this IO. So we take IO is equals to minus VO over RD. Let's say this is equation 3. And we go ahead and plug that into here. In order to see how IO is equals to minus VO over RD more explicitly, you can consider that IO is the current that is flowing from ground, so 0 potential, 0 volt potential, to VO. So this is going to be, another way to write IO is 0 minus VO over RD. As a result, this is minus VO over RD. So when we go ahead and plug that into there, into this equation here, we get minus VO plus RO minus VO over RD minus RO GM Vn is equals to 0. I'm going to go ahead and move all my VOs to the right hand side, and I get VO plus VO RO over RD is equals to minus RO GM Vn. I can go ahead and pull out a VO here. I'm left with 1 plus RO RD. And this is equals to Vn minus RO GM. So then now we can solve for V out over Vn. Again, this is equals to the AV gain, which is equals to minus RO GM 1 plus RO over RD. if I go ahead and multiply this right-hand side by RD over RD, what we're left with is minus GM RO times RD over RD plus RO is equals to AV. So this is your total AV gain of a common source N-channel MOSFET. And we could simplify this, especially when we're doing analysis with bigger circuits like op amps. We can simplify this and say when RO is a lot greater than RD, AV, think about it like if RO is infinity, it's minus GM, let's just say infinity times RD over RD plus infinity is just an infinity. And this cancels out. So this is equals to minus GM RD. So this is the AV gain, or the intrinsic gain of this, or the AV gain of this common source NMOS, N-channel MOSFET. If you find this video helpful, please like, subscribe, and share my videos. In another video posted on this playlist, I have the common source N-channel MOSFET with source degeneration. Please make sure to check that out. Again, please like, subscribe, and share. Thank you.